Okay, so now what happens if we have two slits with a wider width? Okay, so let's just talk about double slits here. But don't forget that in this case, the wavelength, right? The wavelength is just about the same size as the slit width, okay? Or it can be smaller than the slit width as well. Let me just right here. Okay. Then let's talk about the variable that we need to use in this topic, right? Again, so the lambda here just be the wavelength, and the a is going to be the width of the slit. So just the same as this one, the width of the slit. And then finally the d. The d just be the distance between the two slits here. Okay, the d just be the distance between the two slits. This is what we can see from the on the screen. Okay. Okay, so you can see that we can see the bright fringe, okay, and the dark and the bright fringe and dark and the bright fringe. I mean, switch each other here. So what will happen is just from this one. If you look at this dash line, right, dash curve here, it's gonna be the envelope. The envelope from what? The envelope from the diffraction patterns. Okay, as it said here, the diffraction patterns acts as an envelope. Okay, and then this curve is gonna form the interference from the two slits. Okay, so now you can see we have the two effects. I mean, in this case, we have diffraction. It will be the envelope here, and then the interference is going to be this pattern. It means that we can compute the intensity at each position here, right, using this equation. So we need to combine the intensity from the interference, I mean of young double slit, right, and the diffraction from the single slit. Okay, so if you remember the equation, we have the I equal to the I max and sin square beta over 2, where the beta equal to this guy. So this guy, the A here, is just the width of the slit. And then for the young double slit, right, we have the I equal to the I max and cosine square phi over 2. So phi equal to the 2 pi over lambda, and then times the d sine theta. This d is be the distance between the two slits. Okay, so if we combine this equation and then this equation, right, and then this equation, so finally we can get to be something like this one. Okay, but you need to keep in mind that this Imax is not the same as the Imax from the young double slit and the Imax from diffraction by the single slit. The Imax, again, by definition, is going to be the maximum intensity of the central bifringe here. Okay, so this will be the Imax, the maximum intensity of the central bifringe. And then again, we have the phi here, the same as the young double slit, and we have the beta just the same as diffraction by single slit, right? And we just multiply these two terms together. Okay, so now let's understand this one a little bit, right? So we have, okay, the single diffraction, we have the pattern look like this. Okay, I mean, as you have seen already. So the MD is going to be the order from the diffraction. So this just stands from the diffraction. But then on the other hand, if we have the two slits, right, we can get the interference pattern to be something like this one. You have seen this already. And we have the MI to be the order from the interference. So if we combine these figures and these figures together, it will look like this one. So the intensity from diffraction, right, it will behave as an envelope. And now the intensity from the interference is going to be shrink. Okay, it's going to be shrink and to be look like this one. Okay, so it means that the real intensity is going to be this one. Okay, so this is what we've seen. Okay, I mean from on the screen. Okay, So let's look at this example. Okay. Coherent light, okay, of the wavelength, the 501.5 nanometer. So let me just write down the variables. We have lambda equal to the 501.5 nanometer is sent through the two parallel slits in an opaque material. Each slit is the 0.70 micrometer wire. So we have the A, the width of the slit, right, equal to the 0.700 micrometer width. And then the centers are the 2.80 micrometer apart. This will be the D, the separation between the two slits. Okay, the 2.80 micrometer apart. The light then falls on the semi-cylindrical screen, okay, with its axis at the midline between the slits. So we have the semi-cylindrical screen. It just means that we need to compute the angle, right? So we would like to describe the appearance of the pattern of the light visible on the screen. So now for the part A, find direction for each two slits interference maximum on the screen as an angle away from the bisector of the line turning the slit. Okay, actually it's just this picture. We just want to find the theta for the we just want to find the theta for the maximum. Okay. Okay, so now for the part A. Okay, so we just want to find direction, right, for each two slit interference maximum on the screen, okay, as an angle. So we just want to find the theta for the bright fringe, by the interference. Okay, I just want to emphasize from the interference here. Okay, so then we need to use which equation? We need to use equation from the Young's double slit, right? We said that the psi theta m equal to the m and then times the lambda. Okay, the psi theta m equal to the m times lambda. All it means that the theta m, right, equal to the arc side of the m lambda and then over the okay, theta m equal to the arc size the m lambda over d. So this is just easy, right? You just plug in different m and lambda and the d from this one, lambda, the d, and the m into this equation. So now you can get that. Okay, let me just put it here. We can get, okay, for the m equal to the 0, right? We can get that the theta equal to the 0 degree. Theta 0, okay? So now for the m equal to the 1, we can get the theta 1 equal to plus minus the 10.3 degree. So actually I compute for you guys already. And now for the m equal to the 2, right? We can get that the theta 2 equal to plus minus 21.0 degree. For the m equal to the 3, we have the theta 3 equal to plus minus 32.5 degree, and the m equal to the 4. I can get the theta 4 equal to the plus minus 45.8 degree. M equal to the 5. I can get the theta 5 equal to plus minus 63.6 degree. Okay, and that's it. If m larger than 5, okay, so no more maxima, and that's all. So that's gonna be the the angle that we can get, right? And then if the m is larger than the 5, so we don't have the theta anymore. Okay, you can just compute from here. If you plug in m equal to the 6, right, you can get that this term will be greater than 1. but we know that the sine theta should be less than 1, right? So it means that there's no solution for the theta m. Okay, so it's no more the maxima. Okay, now for the part B. Okay, now for the part B. How many angles are there that represent the two slits interference maxima? How many angles that represent the two slits interference maxima? So okay, for each m we have the two angles, right? But now we have 1, 2, 3, 4, 5. We have the 5 m's. Okay, so it's equal to the 2 times the 5, so it means the 10 angles, and then we need to plus the middle one, right, which is equal to 1 to 0 degree. So then finally equal to the 11th angles. Okay, so it means that we have totally the 11 angles here. Okay, but don't forget that from the part A and the part B here, we just take into account the interference from the two slits, right? We haven't taken into account the diffraction by the width of the slit yet. Okay. Now part C. Okay, part C. Let me use the red. Part C. Okay. Find direction for each single slit. Okay, single slit. Interference minimum on the screen as an angle away from the bisector of the line joining the slit. Okay, so now we just want to take into account each slit interference minimum on the screen. So then we need to use this equation. We need to use this equation, right, to find the angle of the dark fringe or the angle of the minimum. Okay, then from equation the A sine theta m equal to the m times the lambda. A sine theta m equal to the m and then times lambda, right? Or we can get that the theta m is going to be equal to the arc sine and then the m times the lambda over the A. Okay. Okay, so let's compute for the m equal to 1. So don't forget that for diffraction by single slit, we just start from the m equal to 1. We don't have the m equal to 0. From the m equal to 1, right, we have the theta 1 equal to let's see, equal to the plus minus 45.8 degree. Okay, but now if the m is greater than 1, again, so no more minimum. Why say that? Because if you plug in the m equal to the 2, okay, if you plug in the m equal to the 2 in this equation, you will get this term to be greater than 1. But we know that the sine of the theta must be less than 1, so it means that there's no solution for the theta. Okay, so it means that we don't have any more minimum here. Okay, then for the part D, we want to find, how many angles are there that represent the single slit interference minimum? Okay, so that's simple. We have the two angles, right? We have the two angles because the first one is positive 45.8 and the second one is negative 45.8. So that's why we have the two angles here. Okay. So again, I just want to emphasize one more time that this one, this one just come from the interference of the two slits, right? Interference of the two slits. Okay, and let me just draw the arrow. And this one just represents the bright fringes. The bright fringes from, okay, let me just write it this way. The bright fringes from the interference of the two slits. Okay, And now this one just represents the dark fringes from the diffraction of the single slit, right? Due to the width of the slit. That's why we must have the diffraction here. Okay, that's it. Let me use this color. Okay, A, B, C, D. So now the next one is E. How many of the angles in part D are identical to those in the part A? Okay, we just want to compare this one and then to this one. So we can see that we have the two angles overlap to each other. So we have this one, right? And we have this one overlapping to each other. So that's quite simple. We can say that we have the two angles, right? The two angles, which is the plus minus 45.8 degree. Okay, so then part E, part F, how many bright fringes are visible on the screen? Okay, so I mean, to understand this part, right, let's just write down the pictures. So we said that we have totally I mean the 11 angles, I mean from the of the bright fringes, right, from the rest of the two slits. So let me just draw the picture for you guys first. Okay, one, and then let me just make the copy. Yep, and duplicate again. Nope, it doesn't look nice. One more time. Okay, we have here. Nope. Okay, this should be fine. Yep. Yep, this is much better. Okay, 1, 2, 3, 4, 5, 6, 7, 8, and we have we need 3 more, right? We need 3 more. Okay, duplicate. Okay, that's it. And okay, so let's just write down the angle. We have this one to be the 0 degree. Okay, and we have this to be what? Plus minus 10.3 degree. So let's say the 10.3 degree, right? And the next one is 21.0 degree, and then 32.5 degree. Okay, and 45.8 degree, and then finally the 63.6 degree. Okay, on the left hand side just to be the same. Okay, so let me just take the note first that I mean this is the central maximum. Yep. Okay, this is the central maximum here. And then this will be the m equal to 1, 2, 3, 4, and 5. Okay, so don't forget that I mean the blue the blue color here just represents for the interference, I mean of the bright fringes, right? But now for the diffraction of the single slit, let me just use the red here. So you can see that we have only theta equal to the 45.8 degree, right, to be the minimum or the dark fringe from the diffraction by single slit. Then it's just gonna look like, okay, this position, right, and this position is going to be the 45.8 degree. So it will look like this one. Okay, yeah, let me copy because I'm not good at drawing here. Okay, and then, oops, wait. Wait, just curious. Okay, that's fine. Okay, let me draw again. It's gonna look like, yep, okay, kind of symmetry. Okay, and it's gonna go for like this. Okay, kind of. Okay, cut off like this one. Okay, so the red one just represent the diffraction pattern from the width of the single slit, right? And then again, this angle just be the 45.8 degree. Okay, so don't forget that this one, right, is going to be the envelope. Okay, the envelope of the total intensity. It means that the blue pattern, okay, the blue pattern here from difference will be trimmed to the size or to the height of the red one here. Okay, just the same as this picture that you have seen it already. Okay, so now the question of the part F, right, is how many bright fringes are visible on the screen. Okay, so if you look at this one, you can see that at this angle 45.8 degree, this one and this one, right, we'll just go to the zero. It's gonna be the minimum because it's just controlled by diffraction pattern of the single slit. Okay, this angle. So it means that finally we have only 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so finally we will have only the 9 angles. The nine bright fringes. Okay, so this will be part F. Okay, we have only the 9 bright fringes, okay, on the screen. Okay, so now part G. If the intensity of the central fringes is the Imax, what is the intensity of the last fringe visible on the screen? Okay, so it said that if this value equal to the Imax, okay, we want to find the intensity at this position, at this angle. Okay, we just want to find this value. Okay, we want to find this value. So that's quite simple, right? We just use equation of the intensity from the diffraction. Okay, so it said that the I, right, and then over the Imax is going to be equal to actually you can use this one as well. Okay, but don't forget that because right now at this angle, right, at the 63.6 degree here, you will have the maximum from the interference. So then you will get that the cosine square favor 2 is just be equal to 1. Okay, so you can use it and go, and then finally you will get this equation. Okay, but for the simplest, let me just use this equation. We have the sine, right, of the beta over 2 and then square. Okay, we have the sine of the beta over 2 and square. So let's compute. Okay, let's talk about the beta over 2 first. Beta over 2 is just equal to the pi over the lambda, right, and then times the a times the sine theta. Okay, the pi over the lambda is equal to 501.5 nanometer. The 501.5 times 10 to the negative 9. Okay, and then times the a. The a is what? The a is 0.70 micrometer. Times the sine theta, so it's with the size of the 63.6 degree. Okay, so this will be the beta over 2, and you can get that it's just equal to the 3.93 radian. Okay, so don't forget that it must have unit as the radian here. Okay, let me move this up a little bit. So then finally you can get that the I over the I max, right, is going to be equal to the sine. Okay, let me just say because the sine is the sine, right, the size of the 3.93 radian, and then over the 3.93 radian here, and then square. Okay, then it's going to be equal to 0.0325. Okay, and that's going to be the answers. Okay, that's going to be the answers here. Okay, so that's all for these topics.